so far not put every unit, but let's read the general system layout. But
It's fine. I'm saying
I have loaded the system layout and started like do it for me. Not really. Well, like ChatGPT was the proper code is not kind of good, so I just don't probably. The one I put on LinkedIn is like very similar to the one I was looking at. Like,
I saw your post about but they're almost going to place them. Because the Anthropic team and because you like features.
So, like 25 years later, I probably could do that.
Let's see.
Open the eye with the fall.
Okay, so good morning, everyone. Assalamu alaikum. I think we can start. So last time we stopped at this slide, but before we delve into some of the technical contents, again, I want to revisit some of the logistics and then the course as a whole, maybe refresh your mind about what we're trying to do in terms of learning outcomes, and also see if you have any questions or concerns. Right? So some information about, I forgot to add this. Okay, so well, some quick info. So I did post the scheduling problem solution yesterday. So hopefully you have access to them. I did solve them yesterday, I think midnight, and then using different pen, like my Microsoft pen. So just make sure you also revise, right? Like in case there's something wrong, just come talk to me, right? I did double check them twice, but I wasn't feeling very well, so you never know. So that's for the scheduling problem, which means right now under the exercise questions folder, you guys have scheduling problems, the UART and the sensor stuff, the interrupt stuff, as well as the embedded questions, right? Which more or less really all the topics that will come in the midterm. Good. Some of you already asked me to see if I can post more problems. I will see if I can do this sometime today or tomorrow. I don't promise, but you already have enough problems, in fact, in your plate. If you are able to solve all of this and revise the examples we have in lectures, in fact, this is all what you need, right? And again, the midterm level will be more or less the same as the average of the quizzes, right? So no surprise.
Actually, the midterm is like the quiz.
I did not say that.
You said the average of the quiz.
I said the level of the midterm, right? Like that, you mean like in terms of complexity, it would be more or less similar to average of the quiz 1 and quiz 2, right?
So a midterm is just a long quiz.
I mean, if you want to have a definition for the midterm, I can talk about this later on, right? But this is not what I'm trying to say. What I'm trying to say is more about the level of complexity. Some of you asked me also, is it going to be similar to the quiz or different, right? I mean, a quiz is an exam, a midterm is an exam, and final exam. So if you want to define it, is a midterm a long quiz and final is a long midterm? I don't know, right? Maybe I can go into these arguments after the lecture.
It's amazing. Philosophy is amazing.
Exactly, right? I was saying there's things that you'll never be able to find a correct answer. Yeah.
I find the quiz easy.
That's good.
Will I find the midterm easy?
If you find the midterm in the quiz easy, then probably yes. Find the midterm. Then for the presentations, as I asked you on the other section last week, I think there is more or less like an unanimous agreement that you guys want to be in the project, not in the more application sites, which is okay to me. That said, we want to be very sure what you're really to expect from the presentation, right? So the presentation about the project is not the demo, right? You are not asked to talk about how did you do things. This is going to happen in the demo in the lab, right? The purpose of the presentation is similar to if you work in a very big project in industry and you go talk to your managers about what you have done, right? Usually you don't delve into all the small technical detail wiring stuff. That's not the purpose. The purpose is to show them a block diagram of the project, what you're trying to achieve. How did you achieve this? Like how, not in technical difficulty, but more into the interesting parts you faced while you are developing the project, right? Why did you do things in a certain way, right? But I will post all of this money into announcements. Don't worry about it. With more details as well, right? So the presentation is not the demo. You want to focus on the scientific aspect of things. Why did you do it the way you did it? Not how did you do it? Good. Just to help you, I'm going also to to post on iLearn, more or less like a template for the presentation. You don't have to follow. I usually don't like to dictate these things, but take it as an example, right? Like I'll tell you, for example, what I expect. This is like a 10-minute presentation plus 5-minute questions. For the 10-minute presentations, or other components I'm expecting to see in the presentation, right? But feel free to creatively build your own presentations, right? I know everyone has his own style. Some people are more visual, some are more textual. I don't care about the style, as far as you deliver the information correct, right? Yeah, some examples, see, for things that I would expect to see, project block diagram, why did you need every component, some of the learning outcomes you have learned across the project, because that's the most important point. And the presentations will be in the last 2 weeks, week 13 and 14, right? Because of the transitions between the groups, I'm budgeting more or less for 1 hour a lecture, which means if you talk about 4 lectures, it's like 4 hours. This gives us more or less like a 15 minutes for every group, right? To be in the safe side, right? So we'll do it in the best, in the last 2 weeks of the course. Now, when exactly is going to be your own project presentation, right? So what I'm going to do is give you a link on iLearn for like a sheet, Excel sheet, Google sheet.
Yes.
And then there will be numbers there, group numbers. And then you guys will insert your names, all the member names of the group. And based on the number you will take, I will do a mapping and assignment, right? Like I would say, for example, I don't know, Monday, XX November, from Monday, what lecture? 11. So from 11 to 11:15, it will be group 5, for instance. Good. So you will have an exact slot what you expect to present. I don't like this to be like first come, first serve or any mess. I want you to know exactly when are you presenting and be ready, and we don't have a mess in the class. Good. So this is our way to organize those slots. Any questions so far? Yeah. Yeah. So for example, you are the only one from this section, then you can attend to the other section, and then that's okay, right? Can they attend in your own? That's an interesting case. So let's discuss after lecture. Is there any other case like this? You guys are from different sections, but you cannot attend, like all the group cannot attend either here or here.
Yeah.
Yes or no?
I think my 2 members are not here.
Yeah, but we can.
What I'm asking is that are they on the same section or not? And if they are not on the same section, will you be able to attend or they will be able to attend? But again, let's keep those cases. We can talk about them one by one.
What time is the next lecture? What time is that?
It's Tuesday, Thursday, 9:30 to 11, 10:45.
Yeah, 9:30, I for sure cannot attend because I have a digital electronics.
Yeah, talk to your group, come talk to me, and we'll arrange it.
Professor, since I had just like maybe fun suggestion, since there are like just 3 or 4 different classes of projects.
Yeah.
Maybe we can mix up the classes of projects when we have a schedule, because otherwise, like if there are 4 projects of the same class of projects, then it would get
You mean types of projects?
very redundant. Yeah.
Yeah, I mean, this is part of the mapping I will do.
Okay.
Right? So leave this to me.
Oh, I thought that.
Yeah. I will see how I look at it.
Will the presentations only be during class time?
Yes. Any other questions? Yeah.
Can we use a teleprompter?
Can we use?
Teleprompter.
I'm not sure what it is.
Okay, so like, you know how like, when the president gives a speech, he has the rolling text?
Yeah.
I like to do this too.
It's not after the lecture. Okay. Any other question? Okay, good. So that's with regard to the presentations. One thing to mention is that attendance, unlike my style, that attendance is not mandatory, but this for when I'm talking, right? I'm okay, not one, like if you don't want to attend, you are busy, you look into the recordings, it's fine, right? But when your colleagues are presenting, I will ask you to come out of respect to them, first thing. The second thing is, in fact, it's a very good learning experience for everyone. When you are sitting down, relaxing, and then listening to the colleague that is presenting, you will be able to learn something, maybe good or bad, but to avoid and good to adopt, right? So we learn from each other, right? Because of the class number, it's very hard to do, again, dynamic classes that we learn from each other throughout the semester, but let's leverage this opportunity that you come and attend and listen to others, do see what they have done, right? We have a very diverse kind of projects from everyone. They are very interesting from those that came talk to me. So I think it will be interesting to come. And also, you come and ask questions. Part of the evaluation that in your, like there is a 5% on this presentation. You will do the presentation, that's part of it. but I will reserve some sort of way into you being interactive and asking your police questions in that lecture. Good. I want it to be interactive and simply you just enjoy it and learn from it. Good. That's for that attendance. What else? We said it's 10 minutes plus 5 minutes, plus or minus. Make sure you stick to time. It's very important. It's part of the evaluation, right? Part of the presentation skills. You must stick to time. That's about the presentation. So I'm going to move to the midterm. Is there any question, concern about the presentation? Are good? Yeah.
What about the final project report?
Yeah, that's a good question. So the presentation is in class. The report and the demo and everything is associated with the lab slot time, right? So this we will give from Salsabi, we are arranging the background, and most probably I will come into the demos as well. Yeah.
There won't be any presentations in the lab, I'm assuming.
No presentations. You will be demoing stuff. You will come into you, we show us it's working, we ask you questions, but technical questions. How do you do this? How things go? Can you explain this code to me? Things that we will not be able to do in the presentation. So they should be complementary to each other, right? The demo is more into the technical aspect. It's like we're asking you, explain this line of code. The presentation is more like the high level stuff, right? One reason. Yeah.
So the presentation will be the last 2 weeks, them also the same time or?
Yeah.
Same time.
Yeah, but put in mind that I think the demo is in the last week, if I remember
Yes,
correctly.
will be after the presentation.
It will be after or before they are orthogonal to each other. Because again, I'm not expecting you to have the full, if you have this fully working, that's great by week 14. But some of you might be presenting on Monday, week 14, where you still have 2 weeks more or less to work on the project. And this is also another aspect into it. The presentation is not about how did you do the project, right? It's not about the technical aspects. It's more about the high level. So the high level should be by now finalized, right? And it's too late to do this, right? So maybe, for example, you are fixing a problem. Don't come to the presentation and undermine yourself and saying, well, but we're still fixing a problem there. It's irrelevant, right? The presentation, when you go to managers in a company, you don't talk about the dirty language, right? You just talk about, well, this is our vision, this is what we have done, and then maybe this is what is remaining, it's okay, right? But just you focus in the abstract level of things. Good. Any other question or concern or suggestion? Good. The attendance today is good. So that's good. We don't have a quiz or midterm. It's interesting. Okay. So if we have no more questions for the presentation, for the midterm. So the midterm is on Wednesday. This Wednesday as planned. We'll take the whole lecture. So make sure you come in time. Now again, I keep saying this maybe for the 3rd time. If something happens, as an emergency happens, because again, there's some sort of hectic situation in the background that I might just need to leave the maybe even in the middle of a lecture, I just leave immediately. Then if something happens, I will let you know, right? But other than this, we are planning for Wednesday. This Wednesday for you and for the Thursday for the other section. Good. The midterm is up until the end of lecture 7, as we said before. For those that just came, again, there are the exercise problems on Avenue, including all the solutions. Even including the scheduling problems we posted last, are already on iLearn now. Yeah, if you have any question, feel free to come to the office hours. My advice on how you really plan for this, go through the slides, make sure you solve the examples yourself in the slides, and then go to the exercise problems. Don't look into the solutions. There is a reason why I'm really separating the questions from the solutions documents. For every single exercise, there are 2 documents, the questions alone, and then the solutions alone. Don't feel that under pressure, I'm studying right now, I will look into the solution, see how it's going to be solved. It doesn't work that way. You have to solve them yourself because there's a lot of, I would say the devil is in the details, right? There's a small trick here or there. If you just really read the solution, you will be able to capture it. But if you try to solve it and you hit it, even if you don't know how to do it, you go to the solution. Now it sticks into your mind, right? That I don't know how to solve this. This is a trick. If you have it in the midterm, you'll be able to get it. But if you do the slides, as well as the exercise problems, that's all what you need. Good. Any other question?
Why slides and exercise problems? Why not exercise problems only?
Because the course is not the exercise problem. The course is the slide plus the exercise problem.
Because now you make me feel like there will be theory questions and maybe
Might be. I didn't say no, right? Yeah, might be.
or maybe the exercise can.
Yeah, you can bring calculators. Similar to Quest 2, you can bring calculators, but just basic ones, no programmable ones. Again, it's a closed book exam, no electronic devices at all, no smartwatches, nothing, right? But basic calculators can be allowed. Yeah. When is quiz? You mean, we are already done with quiz two. Quiz three, yeah. So this week we have the midterm, next week we have the quiz three, and then the week after we have quiz four, right? Again, if everything goes as planned, right? Good, so this is week 10, 11 is quiz 3, 12 is quiz 4, and then 13 and 14 are the presentations.
How is that just weekend? You got midterm?
How is?
I got midterm on Wednesday. We have a quiz next week as well.
True, because we have 2 quizzes remaining, right? So remember that, again, out of the 4, we have 4 quizzes and the midterm. Again, you can have the dedicated schedule in the syllabus. I'm going to open the syllabus in a second. Out of the 4 quizzes, we are taking the first 3, right? So we have to have 4 quizzes. Again, if something comes up and mixes up our schedule, I will talk to you. But the plan right now is to have 4 quizzes, 1 midterm.
Can we do just 3 quizzes?
And that's your option, right? You do this and you are sure of yourself that you're getting the full mark, but you are losing in reality, I would say the slack of getting the best 3, right?
Also, we have very, like, there's a lot of exams.
I do understand. That's a good point. But put in mind is the following. If I'm thinking, and again, I'm going to think with you, right? This is during lecture time anyway, and you're coming to lectures. Good. You need to study for the midterm and the final anyway, right? So it distributes your study time. And then you are giving yourself an option that if you didn't do very well, then there is an extra slack that I can really find, right? So if I were you, I would just come to the quiz. If you choose, well, I'm very backed up and there is 1 quiz I'm going to miss, that's your choice. I mean, there is no penalty for that. Again, I'm going to take the 3 and that's so.
Yeah, thank you.
Good. So, yeah,
What type of questions should we expect? Like,
for the midterm.
would there be like coding?
Yeah.
We memorize any theory?
Okay, so first of all, no coding similar to labs, right? Again, I will not ask you to write programs, right? This course has elements, basically learning elements or education elements. The lab is a big element of it and the project. So I'm assuming you wrote a lot of code there, right? And we're going to test you on this on the demo and the project, make sure you were involved within the project, right? Because it was a group effort. The exams to me, I mean, that's my philosophy, is not the right place to ask coding problems unless it's a programming course. This is not a programming course, right? So I will not take half of the exam time or quarter of it to ask you to write a full program. It's not the purpose, right? So I will not ask, well, go ahead and implement this. What we can do if we're going to touch on this part of the course, which is the embedded C part, is very similar to what we had in quiz 1. I will give you a program that focuses only on the elements that are related really to embedded C, different than the general C that you studied before, and then ask you to trace, find an output, maybe discover a bug if there is a bug, things that basically are on the shot, like in 10 minutes you should be able to solve, right? So that's my style on asking programming questions. Again, pretty much similar to quiz 1. Now about theory problems, right? I think I said last lecture is that there might be some theory questions, but I tend to not to do them too long. So I don't ask state questions, for example, where you write like a page or 2 pages. That's not the purpose. And it's a closed book exam. And I don't like memorizing things, right? What I can ask is a very small, short questions that sometimes I even write in exams don't exceed 2 sentences or 3 sentences, right? Like you just, for example, what are advantages, disadvantages of interrupt? How an interrupt compares to bullying, right? For example, what are the main characteristics you look for in an embedded system? How an embedded system is different than a general purpose system? The very high level kind of intuition that I want you to know by heart by the end of this course, right? And it will be very short bullet points. Good. And usually this is just 1 question at the beginning if it comes, right? Yeah, and you don't have to stick to the language of the presentation as far as you say language correctly, like you don't say something wrong in your own language. I'm going to accept. So don't try to memorize things, rather try to understand it. Did this answer your question? Yeah.
Exercise questions. Does that mean that like there will be a completion question which is in the slides but not in the exercise question?
I never promised that I will bring in the questions exactly from the slides and the exercise. Usually the exam is outside of both. But it's more of the topics themselves, right? The exercise problems are nothing other than an application of what we have in the slides. So they are not different material, right? So I don't want you also to maybe complicate your life by thinking, I have to do these 2 things. In reality, the exercise problems are a direct application of the slides, right? And again, they are very similar to the problems we have in the slides anyway. So they are not either or, right? They are complementary to each other.
Oh, so if I understood the exercise questions, then I'm ready for the midterm.
The exercise questions are?
If I understood the exercise questions, and I'm ready for the midterm.
I didn't say that, right? You have to, I mean, if you're trying to get an answer moment from me that can I ignore the slides and only solve the exercise problems? My advice is no, don't do this if you have the time. If you are crunched in time and you only have 1 hour before the exam, this is a different story, right? But if we're talking about planning correctly to study for the exam, definitely start by the slides. This is my plan, and then go to the exercise problem. Right? Any other questions? Yeah. I'm going to open the syllabus. I forgot. There is 15%, 20%.
25%.
I will open the syllabus anyway right now because I want to go through it. Oh, you mean the total grade? No, again, I differentiate between the total grade and the weight, right? Because the total grade will depend on how many parts they have in a question and how to fairly differentiate between different mistakes, right? So it has a different formula for the exam. But the weight itself is what matters, I think, at the end, because it's out of 100, out of 400, it doesn't really matter at the end, right? What matters is how much weight it is. And I'm going to open the syllabus unless you have any question in these slides. Good. Okay. Good. So just to maybe walk you through what we have done so far in the course, because again, we did not do this for a long time. Every topic we start, I mean, we kind of give the big picture again. I'm hoping that you guys are not bored because I think I might be the most instructor that every lecture come and talk about what is the big story that we have for the course, right? But I'm a big believer of this bigger picture. If you capture it, that's very important.
So you're the best instructor.
Good, that's a compliment. Yeah.
Right, really.
Okay, so now, what topics did we cover so far and why they relate to each other, right? If you look into that table that we have in the syllabus and you already have it on iLearn, we started by the big picture of embedded systems, right? The modern applications, and out of the applications, we extracted the challenge, right? That's what we have done in lecture 0 and lecture 1. Good. So just set the stage of what are we really looking for and why it's relevant and important, right? To start. Then afterwards, we ended up this set of lectures by the fact that this is a systems course. It's an embedded systems course or a cyber-physical systems course. So we need to look into all the layers that would constitute that course, right? Which is, again, one of the unique things of that course is that, again, it combines knowledge from different fields because it's interdisciplinary in nature and also it's a knowledge consolidation because you bring in things from architecture, things from programming, things from operating systems, and you put them because you build the system. Good. And for this reason, we can, in fact, split our topics into layers, right? As we have done throughout the explanation. The first layer is the hardware layer, the interfacing layer. We said these are the ears and the eyes of an embedded system. You need to interact with the physical environment through sensors and actuators. So we need to learn about IOs, right? This is more or less like the digital periphery stuff, the IOs, inputs and outputs, sensors and actuators, and then interrupts and pulling, right? These are the set of lectures talking about embedded system interacting with the physical environment, good? The physical nature of an embedded system. And then we moved a little bit higher in the stack, going to operating systems, right? We talked about scheduling, the real-time theory in general, why we care about timing, right? Because again, from lecture 0 and 1, timing is the most important aspect of an embedded system because of the response time and the safety critical nature. And then we had scheduling, and then we complicated the challenge a little bit. There's a scheduling in single processor, periodic tasks, what if they are aperiodic, what if they share resources, and what if we do multiple, right? That's the story of this set of lectures. I think we spent like 3-4 lectures on. And then we moved back to the architectural layer, right? Again, we are concerned about modern embedded systems with their applications. So we said, we solve the scheduling problem by mapping tasks into cores. Good. But those cores will be sharing hardware resources. If you have a platform, you will have other components you need to care about, and you share. This includes interconnect or buses, right? And then caches, and then main memories, right? So we started by the interconnect, the simplest, and then went into caches where you have a more of interactive behavior of hits and misses, and then main memories, the piece we are studying at the moment. Good. By doing this, we are only, once we finish the main memory, we're only left with one lecture that sometimes I do in class and sometimes not based on the time, is inside the processor pipeline itself. What aspects do exist for an embedded system? For example, why it's very common that ARM is the most common architecture in embedded, but maybe, for example, x86 Intel/AMD is the most common in high performance computing. Why that's the case? Why Intel architecture is not suitable for drones or something else, right? That is real time in nature. Good. This angle is simply what we call the CPU microarchitecture. Again, I'm borrowing a topic from architecture course, but then seeing the angle from a real-time aspect. We might do this lecture if we had the time after we finish the DRAM. Good. So that's the bigger picture of things. Now, if these are the topics, so what did we try to learn out of this? What did you try to learn out of? Is it the one? Oh, not this one. Yeah, here. I think if there were few things that you want to really, and after you are done with the exam and everything, and you want to say, what did you really learn about that course, right? What is important about the course? It would be the learning outcomes, right? Again, aside from the fact that this is a formalism that we need to submit syllabus and that stuff, right? I'm not the best person when it comes to routine, right? But I do believe in every single item here that we have, right? Because I wrote them myself based on the past experience, right? So we can discuss together what did we learn and we didn't learn, and what you think maybe is something that you would like to learn more about. So we started by understanding really the basic characteristics of an embedded system, right? I know you have already taken 241 before, right? Which is the basic interfacing course. But usually this course focusing on the low-end embedded systems, right? It doesn't give you, or in my belief, it unfortunately gives you the wrong view about a modern embedded system. It's not because there's something wrong with the course. This is the case for every university, but because you have to start from the simplest architecture before you think about the new challenges that would exist at the moment, right? So you can think of 241 is the fundamental. I need this to know the basics, the interfacing, what is an embedded system, how things work. But there is a very limited application at the moment for this very, very limited embedded system, right? Most embedded systems nowadays, the billion-dollar markets are really very high performance, and they face challenges that you will never be able to discuss in 241. Good. So this was the number one element that we discussed in lecture 0 and lecture 1. What are the characteristics of a modern embedded system and the challenges we need to really redefine that embedded system? Because this constitutes every single technical topic that we discussed in the course. Good. So that's the first element that we discussed. And then second one is more implementing like edge and embedded and that stuff. This is more like a lab learning outcome where you guys interact with the physical environment. Something we changed this year that wasn't there before is we moved on ARM architecture and a more high performance board. We introduced the RTOS thing because it takes us closer to this vision of a complex real embedded system. Okay? And some of you did projects related to connectivity as well. So related to IoT or Wi-Fi connectivity, which are also closer to edge computing. And then again, wired and wireless communication, it happens in the lab since lab 1. And then again, the designing element is also, we discussed the theory of the design and the trade-offs. Again, we talk about sensors, actuators, talked about linearity, noise, right? Calibration. These are factors that if you work for an embedded company that manufactures these sensors, you have to care about. And then you go to the lab and you start really doing not really a design of the components, but a design of the system itself, especially in the project. And then number 5, which is understanding the trade-offs between high performance, like general purpose, the trade-offs that you face when you want to design high performance embedded system. Again, that's one of the defining themes of that course, right? If we only care about predictability or simplicity or analyzability, 241 is enough, right? Very simple system, very accurate at the cycle level. I don't have multiple tasks running, no operating system, very limited interfacing. So it's very simple to analyze, but it doesn't give you the performance that you're looking for if you want to do machine learning video processing in a self-driving car or a robot, right? So most of the challenges we are discussing is I want to achieve performance. So I want a complex architecture, but at the same time, how do I ensure predictability? I want to deploy caches, but I want them to be predictable. So I do partitioning, locking, scratch pad units, right? I want to do main memories, but I want them to be also predictable. So we'll discuss the things we're going to discuss. I want to use complex interconnects, but I'm going to use predictable architectures, right? Like you see that the trade-off. I want to have multiple tasks, so there is an operating system, but I cannot use Linux. I want to use FreeRTOS or any other real-time operating system that predictably schedule these tasks, right? So this trade-off, you will find it in every single lecture, right? And part of your studying should be, when I sit down in this lecture, why it really matters in that bigger theme, right? Because it gives you some intuition or motivation why it's important. And then finally, like using modern real-time operating systems, we talked about the scheduling kernels and periodic tasks and that stuff, the theory in the lecture, and you had like 2-3 labs about FreeRTOS in the lab. And then finally, with regard to the applications, I mean, we did cover a couple of lectures at the very beginning. I had the hope that we do the same at the end. But again, that's okay, because what you do as projects, in fact, is an example of applications, right? but you do it more hands-on, right? So this presentation hopefully still helps in this learning outcome as well. Good. Now the question is, and this is for my own sake of, again, understanding the norm and the theme and for future offerings. What is the most interesting learning outcome to some of you? Yeah.
Okay, so I want to give an opinion that I'm pretty sure the whole class will disagree with. I'm not trying to do that. I think I actually care more the most about number 7. Because like every time I take a course, I think like, you know, the whole lifetime I'm gonna have how this course will contribute to it, like the career trajectory.
Good.
Where am I gonna go?
Yeah, so the application side, of it, which is good, which means to you, more or less the most interesting lectures were in fact the first 3-4 lectures.
Yeah, in fact, actually, I would have preferred having the research papers as a presentation if it were not for the timing issues.
Yeah, because of we are backed up.
Yeah, if I had more free time, I would have actually preferred to read the research papers, but since I don't have free time, let's just do the project, get the grade.
Interest? Yeah, maybe after that, if you are interested, come talk to me, I will share with you a few papers and you can.
The design aspect, I like the idea of these designing the systems and what are the common ways to design it and how it's used in real world, and also edge computing, so that we can apply machine learning or deep learning into these small microcontrollers.
Okay, yeah, that's excellent, but I think most of you didn't reach, I mean, because it's a very packed course, we didn't reach to that point yet. Maybe one thing to mention here is, maybe I didn't mention it before in the class, some of you already asked me. In reality, I'm offering a graduate course next semester about tiny machine learning, how you really run machine learning algorithms into these embedded systems, right? In reality, tiny machine learning is a very new topic. It's like the top notch of machine learning community at the moment. And very few universities offer that course, by the way, right? So I'm going to offer it for the first time next semester. It's a graduate course, but I think from talking to Dr. Imran and others, you guys as undergrads are allowed to take with certain permission or something, right? So the reason I'm mentioning this now, because the topic of that course is exactly what you asked about, Ammar, right? How we run machine learning and more advanced algorithms into these small devices, right? There are a lot of challenges that you will never face when you, for example, try to run a neural network on an NVIDIA GPU, right? Because you don't care about compute power, you don't care about memory
Not on an
limitations.
SDM controller.
Exactly. Good. So that's with regard to the edge computing. Any other? Yeah.
Honestly, I feel like I mostly enjoy it because it really links to the real world and the industry aspect. Because I feel like a lot of courses are mostly into academics.
Okay.
Don't get me wrong, I'm against that. But I feel like, especially if someone wants to plan opportunity in the industry, it's good to know about it. I like number 5 because every time I ask regarding multiple, for example, in the scheduling, multiple different types, why use this one? Why that one? Why is this one best for industry? This one theoretically is better.
Yeah.
I enjoyed that part.
Yeah, that's great. Thanks a lot. And I think that's a very important point because, for example, we mentioned so many times that this is ideal in theory, in formal proofs, in textbooks. But if you talk about industry, they adopt something completely different, right? And that's exactly because of these trade-offs, the cost and the complexity of implementation, what you look for. So I think that's a very important aspect of the course. Yeah, thank you.
Professor, I may have not focused or maybe you haven't teach there. Did you talk about wireless?
So yeah, we did not really, well, not in the course, like not in the lectures, but in the lab, and in fact, in the project. Did you do any lab about wireless communication?
Today is the one about.
Because there was a one that we were planning to do after the FreeRTOS. I think you are done with the FreeRTOS lab.
Yes,
So this week will be the wireless communication. And also some of you already in part of the project are doing wireless communication, right? But there is a lab this week, I think is the wireless communication lab. Yes. Any other comment, feedback, something good, something bad, something you enjoyed more, something we should focus more on when we offer this for the second time? Something when you came to that course you didn't expect to find. I'm hoping by now you changed your understanding of what is really an embedded system, right? That's the most important one.
Okay, first of all, the most surprising thing about this course is that how the lecture is too theoretical and the lab is too practical.
Yeah. Okay,
The exact balance.
okay, that's a good point. Yeah, that's definitely a good point, right? I think
I don't think it's bad, because I think it's
Yeah.
bad because no other course has done that before.
true. Okay, that's a good point. So I will explain to you my philosophy, right? And it might be wrong. Again, maybe I need to rethink about this. One problem is it's a big topic that you want to cover different elements. And you start playing around with the different cards you have in your hand. We have labs, we have projects, we have presentations, we have lectures, right? And we have some exercise problems you can solve. In the lab, I know you guys are immersed in coding, right? interfacing and that stuff. And then I rely a little bit into 4.1 that you have done some of the field work, maybe even in simulation a little bit. But there are angles that you will not be able to touch in the lab, and it's good to know about. For example, in the lab, it's very hard to do multi-core experiments because you will need to spend a lot of time, right? I mean, I have graduate students that spend years to try to get it to work, right? But I want you to learn about the stuff that when you go work for a real company, you have learned about some of these challenges, right? Now, this divergence happens a little bit. What I try my best to do is at least link the topics. For example, when you talk about an operating system, what are the elements of an operating system? Scheduling from the theory side, as well as synchronization and queuing and semaphores in the practical side, right? So this one is more suitable for lab, and this one I will cover more into a lecture. Something we could have done is make the lectures talk about semaphores, for example, but then it will be an implication or intersection with the lab, right?
So it's smart, maybe, it's much covered.
Yeah, this puts more emphasis, but this puts also more load on you guys, because there is much material, like theoretical as well as practical, right? I do understand this, right? But hopefully you will learn more. At least you hear about some topics that later on, if you didn't really do in lab, but you heard about in lecture and you have the slides and you encountered some sort of a job, you go back and say, yeah, I studied about this. I vaguely remember it. I can go back and revisit, right? So you will imagine after 10 years, 15 years, you will not really remember any of that stuff, right? But I think the thing that you will remember is I heard that term before, right? Hopefully at least, right? And then I go back and know where to look for it, right? So it's not a completely new term to you, right? That was the goal. Again, if you have better suggestions how to link both, my only fear I might dilute the course level a little bit, right? To be a little bit more practical, and then will turn out into a 2-for-1 dash rather than really an advanced course. But I might be wrong. Again, these things come with a lot of trials, right? Any other surprises you found in the course?
So to be fair, this course is a mix of two courses, so that's why.
It's a mix of multiple courses. Usually in North America, we call them knowledge consolidation courses, right? So what you do is you are already in fourth year. And if you ask me a right program, in fourth year you come and you stop learning new material. Fourth year is not really the time for new material. It's the time for consolidating the materials into bigger elements. Because if you go and work, you never say, well, I want someone excellent in calculus and that's it. It doesn't work that way, right? You want someone that knows to do or knows to how to go and approach a certain topic. This topic is composed of multiple courses that you have covered in your undergrad, right? And usually you do this in fourth year. You do multiple, like 2, 3, 4, 5 knowledge consolidation courses that combines the knowledge into systems level. And then now you learn how you link them, right? Yeah, so this type of courses, if you look up on the internet, they call knowledge consolidation. I like to categorize this course as such, right? Its purpose is not only to provide new information. And by the way, this is why some of you, for example, in the early feedback that we received in the mid-semester, kind of said, well, there's a lot of overlap with the architecture course, right? Which I do understand. It's true. But the point is, if you think about it, we do not really study the architecture topics exactly as you have done in the architecture course. I only give you the brief background to refresh your memory. And then we look into the aggregates into it when we put it into an embedded system, right? And we do the same thing for programming, right? We touch on some of the programming things you covered in second year, right? And then we bring them into the embedded world. Operating system, the same thing, right? And we bring them into the predictive world. It's why I call knowledge consolidation. It brings in knowledge from other courses, but puts them into context, right? So that's true. There is overlap with other courses. That's in fact intended. I think that's healthy for you, right? For your knowledge overall. Any other comment, question? Feel free to come talk to me after the lecture or during office hours. I'm happy to again learn from you how you perceive things, because again, I learned from you a lot about the other courses you also take, right? So maybe you are doing something that completely overlaps with another course and I'm not aware, right? Just feel free to come and give me some feedback. Good. Any other question, concern, comment? Yeah, so we diverged a lot from the technical discussion, but I think it was a very good discussion. Yeah. I think I'm offering it on Wednesdays 5 to 8 or something like that.
I think it does the Tuesday.
That's the problem with I even forgot whether it's Wednesday or Tuesday. To be honest, I need to look up, right? But I think because it's a graduate course, it's 5 to 8. Yeah. Okay, good. So something we stopped at last time is before the last lecture where we had like half of the quiz and half of the DRAM, we studied the access latency of a request to the DRAM device itself, right? We have seen a lot of variability that we said your best case is something around 18 or 15 nanoseconds. Your worst case is above 100 nanoseconds. And to quantify this, we define what we call variability weight, right? How much your latency varies based on the different aspects of a memory, the DRAM state, whether you are a read or a write, whether you are targeting an open row or a closed row, right? Whether you're targeting the same bank or different bank as other, a lot of variability in the DRAM, which if you were to explain this in one sentence, DRAMs are not in fact truly random access. Good. There's a huge variability that we have in the access latency. Then we said, in reality, this is without discussing at all any scheduling or queuing at the memory controller, right? We're talking about a single request that was elected by the arbiter of the memory controller to go to the memory, but based on the state, it's going to suffer variable latency. Remember from the interconnect lecture, we defined two components of your worst case delay, the access latency itself and the arbitration latency. So when a request arrives to a resource, you have to wait until the scheduler picks you up. This is called the arbitration latency. This waiting time until the point that the scheduler grants you the access, then now you can access the resource. This is called the access latency. Good. All this variability is in the access latency itself. It's not about arbitration, right? And we said for the memory controller, one of the most complex IPs existing in modern SoCs, because it does a lot of reordering and scheduling and intelligence to optimize for the bandwidth. Good. And we started first ready, first come, first serve. Last time we said DRAM is composed of multiple banks, right? For example, in DDR4, you can have up to 16 banks. Here we have 8 banks, DDR3. And we said usually most memory controller architectures would have a 1 queue per bank, right? These are the basic queues per bank. And you would have 2 levels of arbitration. First, there is a level of arbitration that picks up from that queue a request that goes to this particular bank. We call this the intra-bank schedule, right? I want to pick up a request among the different requests waiting to access a certain bank. Good. Now, assume this arbiter picks one request, this arbiter picks another one request, this arbiter picks one request, because you have one arbiter per bank. Which one should go to the memory? Now we use the inter-bank schedule. There are multiple requests pending to access different banks, but only one can be sent to the DRAM. Why only one? Because there is only one command pass, right? Like the actual wiring, the actual bits between the memory controller and the DRAM can only send one command every side. Good. So you have to only send one command. After you pick a command per bank, you have to arbitrate again and pick one command across all the banks. Good. Across the banks, usually it's a simple round robin or first come, first serve, right? Because all the commands are ready. There isn't much of an optimization, so we just do round robin. But the actual intelligence or complexity that we explained last time is within the bank itself. Why that's the case? Because remember, the DRAM access latency will vary a lot between head requests and conflict requests, a row head and a row conflict. A row head will suffer only the cast time, right? And we said that if we go back to our chart, this is a read head request that only suffers the cast reading time. This is a conflict request that also suffers write switch and that stuff. Good. So I want the example we explained last time between first come, first serve and first read, first come, first serve, that you gain a lot of bandwidth by reordering requests such that simply you send the ones targeting the open row. Do you remember that example that we drew, right? So quickly again, maybe in a minute. Yeah, you remove that slide. So assume I have a set of requests. Let's say request 1. And this is targeting row 1. And all are going to bank 0, okay? And then request 2 is targeting row 2. And then request 3 is targeting row 1. Request 4 targeting row 2. Request 5 targeting row 1. And you keep alternating, bing bong. Okay, we call this a bing bong effect. If I do first come, first serve, you serve them in the order of arrival. So request 1 is the first arrived, so I have to serve it, right? We said initially you assume everything is idle, right? So you only suffer. So I gave you like a table last time. You remember we had this traffic light thing, like the green and yellow and red, and we said the green one, the best case, let's say it takes, what are the numbers we gave last time? 7? Forgot what is the number. Conflict. This is your red. Okay, we said no, 70, right? Okay, that's the red bus, 70. And then we said 15, okay, and 10. Okay, good. So these are representative number from DDR4, right? And then I want to see how much latency I take to serve all these requests. If I'm doing first come, first serve, the first one will be a conflict or a mess or a hit. The first one, everything is idle, so it's a mess. Mess means I don't need to pre-charge anything, but I need to activate that row, right? And you suffer 15 cycles. So if you look into the timeline, the first request will take 15 cycles. Then after you are done, again, first come, first serve forces you to serve the one afterwards. You don't need to do any thinking, right? So request 2 will be a row conflict because you are targeting row 2, and the one that is currently open in bank 0 is row 1, right? So how much time I'm going to take? 70 cycles, right? So you suffer 70 cycles, and this is for request 2. What would happen for the rest of the requests? They're all 70 because you keep pre-charging and activating row 1 and row 2, right? So you keep bing-bonging. So you have 70 plus 70 plus 70 plus 70, right? Then you sub up things. Now, if you do first ready, first come, first serve, usually what happens is the memory controller looks into all the queue and first checks if there is any request pending for the current open row, right? In time 0, nothing is open. So you just take the first request, right? So you serve request 1 again, and you take 15 cycles. Now, once I open row 1, the memory controller will go and check, is there any request pending that is targeting row 1? The answer is yes. Even if it's a later request, I reorder it. That's why we call it reordering, right? So in this case, you serve which request? Request 3, right? Because request 3 is the first request that is targeting the open row. Remember, it's first ready, and then first come, first serve. If there are multiple requests pending for the same row, for example, in row 1, I have request 3 and request 5. Which one do I prefer? Request 3, because it arrived earlier, right? So in that case, I serve request 3. How much time I'm going to take for request 3? 10 cycles, because it's a hit, right? We call this a hit. This is a conflict, and this may be a mess. And then the one afterwards is request 5. It's going to suffer a 10. Then the memory controller will go into the queue and check, is there anything pending targeting row 1? The answer is no. What do? Pick the first one, the oldest one, right? Which is in this case request 2. Request 2 is going to be a conflict, yeah, 70. What happens afterwards? Request 4. Is it request 4? Yeah, I'm doing things correctly, right? Yes. Request 4 is going to be a hit, which is 10, right? Now we serve with 5 requests, yeah, total. So if you look up into the total latency, this is 115, right? This is how many? 140, 280. So it's 295. Good. So you saved, in fact, more than half of your running time by reordering stuff. Good. So doing this prioritization of row heads saves you a lot of bandwidth on average case. Good. Now, we didn't stop at this point last time. We said, what is this is for average case. We said all memory controllers existing in our chips employ this, right? What is the problem with this? Like, yeah, correct. But memory control more than one takes data. What you're talking about, that's an excellent point, Amar, that we never brought up, which is data consistency. Yeah. If simply there is some sort of force of order, the memory controller takes this into account because related to the correctness, right? So this is already taken into account. But aside from this problem, when it comes to real-time systems, predictability, what is the problem here?
Problem is predictability only, right? So like you cannot really calculate.
Yeah.
You cannot really determine. So the determinism of your algorithm, there's a failure in determinism.
Yeah. So in other words, it's unbounded delay, right? We said under first ready, first come, first serve. In fact, you can suffer from starvation. If you think about a conflict request, that, for example, this one targeting row 2, nothing is preventing the memory controller to keep receiving row heads into row 1 for a very, very long time, theoretically infinitely. And in that case,
request 2 that is targeting different row or a row conflict will wait indefinitely, right? So it can cause starvation. This is very important for real-time systems because I care about the worst case, right? Not about the average case. Even if average case is good, okay, that's good. But my most important aspect is, in fact, the predictability, right? And we said even modern architectures, because they want to prevent starvation, even if they are not embedded, what they do is they implement first ready, first come, first serve with a cap or a bound. They say, yes, I allow reordering, but up to a limit. After I send a number of requests to an open row, I just stop, close that row, pre-charge it, regardless of how many are pending currently in the queue. Good. By doing this, what did you do? You ensure that there is a bound. But from the real-time angle, this still can be a very long time, right? So this is why when you analyze your first ready, first come, first serve, if there is a request under analysis here, I think I had this slide coming here. One problem would be later requests that arrive after you. If they're open here, I'm receiving to O as like O as open and C as closed. And RUA is the request under analysis. So the request under analysis will not only have to wait for the ones in front of it because of first come, first serve, it will also have to wait for future requests that might arrive, but they are targeting an open row. This reordering impacts your worst case delay. So you have to analyze for it. We call this the reordering component. Good. Now, if you didn't cap first ready, first come, first serve, it's unbounded. There is a proof that there is no bound. But if you cap it, then you are able to drive a bound. Now, what is the trade-off when you talk about real time for this cap angle? Like making it longer or shorter? If it's shorter, what do we gain? Like shorter means, like, okay, I'll just give you an example. Yeah, exactly. So if the threshold is 3 versus if the threshold is something like 30. Threshold means how many hits I allow before I close the row. If I only allow 3 hits and then I close the row, what is the disadvantage? You lose performance, right? What is the advantage? But in 30, you also don't starve because there is, starve means I never get serviced theoretically. But your point is that my waiting time is in fact reduced, more predictable, right? You have a tighter bound. Your worst case becomes now shorter, right? So if I reduce the threshold, I have better worst case, but I have worse average case. So you improved, like if we go back to our diagram here, this is your worst case, and this is your average case. You improved your worst case, but you worsened your average case for the case of threshold if the threshold is low, right? Yeah, you make them close. So you lose in the performance angle, but you gain in the predictability angle. Now, if I made the threshold high, what is the point? What is the gain? Performance, because you keep a lot of row hits, then in this case, you improve your bandwidth, but your bound becomes way higher because now my request under analysis needs to wait instead of 3 requests, I need to wait in worst case for 30 requests before I can get access.
So, so that way, like, your thinking was like, for instance, if there is some certification authority, they would really hate first ready, first come.
True. Yeah, but if you cap it and you show them that you are within your bound, so usually what we do in real time is you can argue, for example, we propose a certain architecture that says this cap can be in fact programmable, configurable, based on the task worst case execution time. So now you link the requirement and you do some math, and based on this requirement, you set the cap that satisfies all the requirements. In that case, you tell the certification authorities, I balance that, which is an optimization problem at the end. Yeah.
It's like an adaptive cap.
It's like an adaptive cap based on the use cases. Yeah. Good. So that's the reordering, what we call the intra-bank. So now what type of interferences we suffer within the same bank? First of all, if even there is no reordering at all, everything is targeting a closed row, we still suffer the first come, first serve aspect. So this request under analysis will have to wait for the conflict requests in front of it. Good. This is what we call the intra-bank conflict requests. These are requests that are targeting a closed row as well, but they arrive before me. Remember, we're doing first ready, first come, first serve. Whoever arrives before you will get service before you if both of you are conflict. Good. So this intra-bank conflict request is in fact the C part. Now the intra-bank reorder request is the O part. Now you can see that the O part, they don't have to come before you. They can come after you, but because of the reordering, they can get service. Then for the interbank, now we said we have multiple banks, 8 in this scenario. And assume I picked up one request under, and finally, after some bound, my request under analysis was picked up by the arbiter here. So it is ready to be sent. But on the same cycle, many of the other banks are also having ready commands. So I still need to do round robin among the banks. And hence you suffer the other interbank component, right? And for the interbank, there's an interbank close and interbank open based on the one ahead of that each bank queue. Finally, some modern memory controllers also for optimization purposes. Remember, we said the DRAM, to make it low cost, your data bus is unidirectional, right? So if you do reads versus writes, there is a turnaround time. There is a very long time, right? If you go back here in some of our timing constraints, this is a read request. Maybe I just show you a head case. Yeah, here. This was a write request, right? W0. And this is a read request, R1. So this is a very long time waiting for between the write and the read, because you need to wait for what we call the switching time between reads and writes, right? The switching time, I need to transfer the write data first and then switch the bus direction from write to read, called WTR, write to read delay. Good. Again, why? Because I don't have separate read and write buses. Why DRAM don't have a separate read and write buses? Because other memories do have, because of low cost, right? Cost is the biggest design element in DRAMs, right? Everything is done to make the cost low. Good.
So what cost to make it the one directional?
You make because you have less number of bits. If you work separate direction, you need two buses, in fact, one for read and one for write. Yeah.
So I think the switch delay, like what are they doing within this time?
What they do, that's a good question. Now I will borrow some, I don't know how many electronic courses you guys took, because I think they are mostly in the electrical department, but there is something called termination in VLSI. What is termination? Especially for very high speed. Like if you connect, you go here. Here, there is a connection between the memory controller pins and the DRAM pins, right? Like if you look into the board, we said there is this layer here. This is the on chip. This is your CPU and caches, last level cache. And then finally, there's the memory controller, which is your interfacing part to the DRAM chip. And this is more or less a trace on the board, right? This is an off-chip bus, right? Now, this is operating at a very high speed. We said DDR4 operates at 2.6 gigahertz, right? Very, very high speed. So to enable things to run in high speed, there's a lot of electromagnetic effect. When we study electronics, you know that there is something called inter-symbol interference, for example. There's a lot of details if you operate in very high speed, what precautions you take into account, how you design your circuit, right? To avoid noise, yeah. And so part of this design is what we call termination. Termination means if there is a bus that operates at very high speed, you have to terminate from here and here to avoid the resonating, like the resonating back. Because if you send a very high, like if you send a signal on a very high speed bus, there is a lot of backward effect that will happen because of the ISI. How we will prevent that? This is like an echo. Like I talk, like it comes back. How do I prevent it? I do a termination circuitry. Termination. The simplest termination circuitry is some sort of a resistor and other resistor and then a voltage source transistor, right? Very simple circuit, but it's very known. It's also used for waveguides, like in communications. Termination is very common topic in very high speed circuit.
Yes.
Now, this termination will depend on which direction I'm talking to. If the direction is going to this, I will terminate here. If termination is coming this, I terminate here. So doing read versus write is a bit different.
So the terminating is so that I don't echo back.
You don't echo back, yeah. So now what the next step I want to convey is the termination will depend on whether you're doing a read or a write. Because if you're doing a read, your direction is in fact from the DRAM to the memory controller, right? Because you're reading data, right? If you're doing a write, you are in the other direction. So in that case, your termination circuit needs to be modified, configured. This configuration takes time.
But this termination exists also.
It exists on the other in the memory controller side. So in that case, you need to switch and take this into account.
So which one needs?
Write to read. Write to read is a way longer delay. Usually write to read is 18 cycles and read to write is like 7 cycles or 8 cycles. Yeah. Compare this to if you're doing write and after a write directly, it's just 4 cycles. Read after a read directly, just 4 cycles without switching. Write and after another write command afterwards, which means the same direction, right? Right. So now, understanding this complexity, a memory controller. What did I do? Okay, so a memory controller will also try to optimize for this scenario, right? If I know that when I switch request types from reads or writes, I will take a long time as a memory, if you are thinking as if you are a memory controller, what you would do, you would try to minimize the switching time. If you look into your queues and you have a bunch of read requests and bunch of write requests, what you will do, if you are serving, if you serve a read right now, what you will do, you will favor a read or a write? A read, and you'll keep doing this for some time. Once you switch to a write, you want to stay for a write for a long time, right? We call this batching solution, right? And again, most high performance memory controllers at the moment do this. They do what we call write batching, right? They favor simply at one point of time, I do a lot of reads, another point of time, I do a lot of writes to minimize the turnaround time. Good. Now, why this is problematic for worst case scenario? If you have a critical read, what will be your absolute worst case?
All the rights.
Yeah, you have to wait for all the batching of the writes before you switch to a read, which is very, very complex, right? So most predictable memory controllers, in fact, avoid doing batching, right? Because again, the batching impact is huge on the worst case. Right? If you do batching, then you separate the read and writes into read queues and write queues, and then you do what we call read write skew. Good. Yeah. Summary is all these optimizations are again very good for average case, but they cause a huge variability in the memory access time and arbitration. Good. So what do? You either analyze them. So you either try to say, okay, they are complex, but I will bring in the expertise. I will sit down and I will try to find bounds, right? Again, if I cap the first rate, first come, first serve, I do something. If I do bank partitioning, I can try to come up with a bound. So you take the existing architecture as is, but you try to drive a bound on, right? Or you try to basically redesign the whole memory controller from the beginning, right? And both approaches, in fact, do exist, right? Some companies and some researchers would say, ignore the high performance memory controller, is very, very complex, it doesn't help us. I'm going to design something from the very beginning to be very predictable. Now, let's do an exercise together. If I was designing the memory controller from the beginning, given all the optimizations we discussed, I'm going to list the optimizations together and we think about them. So the first thing is we said we favor the hits by doing first ready, first come, first serve. So this is basically your hit reordering, right? And then we said you do read-write switching, batching, to simply optimize for the turnaround time. And then, you do a round robin among banks. These are the three things we discussed, right? Now, this is high performance. If you want to go for real-time memory controller, and you have the freedom to redesign it from scratch, first ready, first come, first serve, what I will do instead, put a cap, that's one measure. But if you want to go for just simplest predictability, because the cap would still assume, for example, you ignore about performance. That's maybe the point. I'm trying to take the other extreme. I don't care about performance, it's all about predictability. What do I do? First come, first serve, and no even open policy. Like I just make every request close, right? Which means, remember we said for the open page policy, it's maybe something to discuss here. So let me explain this. We said modern memory controllers, what they will do is if you have a request that is opening a bank, like you do an activation and you do a read, I don't pre-charge immediately. I keep the row open in the sense amplifier for future requests, right? This is called open page policy. It's open page because you leave a page and a row is simply the same terminology in DRAM, okay? And by the way, a page in DRAM terminology is different than a virtual page. It's not the 4 kilobyte thing. They are referring to a row, okay? So this is called open page policy or open row policy. So I keep the row open, I don't pre-charge it. Now, for future requests, if it's a hit, it will only be a read. If it is a conflict, what I will do, you have to pre-charge and then activate and then do your read, right? This is a hit and this is a conflict, right? So we said the problem with open page, the good thing about open page, if the coming request is targeting the same row, you save a lot of time. But if the coming request is targeting a different row, it is the one being penalized for the pre-charge, right? Now, this is an optimization for average case. If I was doing maybe a more predictable memory controller, or I don't want to deploy this optimization, I will do something called closed page policy. I will say, I will not wait until a request comes and it suffers this pre-charge time. After every single request, I activate my row, I do my read, and I pre-charge my own row. Is that the absolute worst? That's the question. It's consistent, but it's the middle part. Like if you think about it, and this is a point that is, I think, worth discussing. So I do the activation, I do the read, and then I do my pre-charge. Now for the coming request, if it is a hit, now there is no concept of a hit because I already closed the row. The first command of the new request will be what? Yeah, which the first command of a row miss is an activate, right? So you have to activate that row. And then simply do your read or write. Now, will it matter whether this is targeting the same row or a different row? You are activating because, in fact, there is no even open row at the moment, right? Now, what Ammar is saying is that, well, I'm now taking the worst case of everything, right? For everyone, I'm doing the pre-charge. That's not fully true. And I think this would require your attention a little bit, right? I promise that this is the last concept we'll discuss today, and then you guys can leave, right? So we still have 10 minutes, which is good. But this is very important to understand, right? Because there's a big trick, but again, it might come to an exam. I'm just saying this to bring your attention. So the point is the following. Open page policy keeps the row open without pre-charging it, which means this request, in fact, will not be responsible for the pre-charge. Why? Under the hope in the future that I'm not even needing to do the pre-charge, right? For example, for this read. But from a worst case angle, for predictability, there might come a request that's a conflict and suffer that pre-charge. So this pre-charge is in the critical path of this request because you cannot do the read before the activate, you cannot do the activate before the pre-charge. Now, closed page policy is saying, well, this pre-charge is not in fact about this row at all. It's about this old row. So for this request, I will tell it you are not really done with the DRAM until you pre-charge your own request. Now, it looks like we're just taking this pre-charge from here, putting it here. But if you think about it, this request is doing its read before it does the pre-charge. So the pre-charge is not in the critical path of reading the data from the memory, right? Which means the data will be transferred to the CPU. So your worst case of this request is not up until here. Your worst case, in fact, is up until here, right? Because I did already do my read, right? So you transfer your data here. So this request latency is this one. So the pre-charge is not part of this worst case delay, right?
You already got the data.
You already got the data, so I can do the pre-charge in the background. But what do I gain? In the future, every single request will find every row is idle, and in that case, I only suffer the consistent time. So if you think about it, we had these three traffic lights for the open page. For the open page under the locality concept, they say, you know what, I keep fluctuating between here and here under the hope that for locality, I'm staying here most of the time, right? So like 80, if I'm 80% hit, 20% conflict, I'm good. Let's keep it open page. Closed page says, no. I don't want to keep variability between up and down. I just stay in the middle. Everything is idle, everything is pre-charged upon a time, and I'm done. Good. So it's more predictable. Yes, you suffer more delay, right? On average case, you don't leverage reordering and optimization of heads. So the bandwidth, the average case of closed page is way, way worse than open page, right? But for predictability angle, it's way better, right? So that's the first design element that for first read, first come, first serve, you know what? I don't like it. First come, first serve. And this is with open page. I'll do this with closed page, right? So what are we doing here? Again, taking an existing high performance memory controller and say, if I was to ruin it and redesign a one for predictability, we're good, right? Second one is this read-write batching. I already give you the answer that most predictable memory controller, in fact, don't prefer it, right? What do? You have a read, schedule it. You have a write, schedule it, which means in worst case, you will always suffer one read-write switch or one write-read switch. The benefit is I don't suffer a lot of batching delay. If I'm a read, I don't wait for a very long trail of writes. It's only one in worst case. Good. So no read-write batching. What about round robin among banks? Do I keep it? Do I remove it? Do I do something else for predictability? It's predictable. We know from interconnect round robin is good. We just keep it, right? There isn't a lot of intelligence or reordering. Round robin is good, so I just keep round robin, right? So this is a typical memory controller tiered towards predictability, not for performance, right? So we now have two extremes. One that disables all the optimizations, redesigned from scratch, gives you good bound, but it's not good for average case. Another one that is very, very high performance, full-fledged of reordering and scheduling, but it's very hard to analyze, or maybe some, if you don't have like first rate, first come, first served cap, it's even unbounded. Good. So that's the first element here. Redesign your memory controller for predictability, and you do this. Second one is say, well, here I'm losing performance, but I need really the performance of the memory because it's the bottleneck, as we discussed earlier. I need to do a lot of machine learning and data reading. Then let's keep the high performance one and try to bound it, try to drive a bound, right? And that's more or less the things we discussed here. How do I drive a bound on the first first come, first serve? Put a cap, see how many open ones you wait for, how many conflict ones you wait for, and do a lot of math, right? I don't want to go into the details of how I really bound it in detail because it's very complex math. But we have a numerical example problems that we're going to solve, hopefully next time, that will show you if we were doing a reads and read heads, write heads, how do we really drive a worst case for a simple scenario, right? Pretty much similar to what you might face in an exam or a midterm or a final. Not a midterm, the final. Yeah.
Professor, like everything that we are doing right now, like coming back from the frame of reference of a DRAM, like looking at everything that we do is so abstracted, like it's sometimes hard to believe that such a system would work so coherently. But how does that work?
How you add components together? Yeah, that's a good point. So our frame of reference of operation again is worst case. Today I saved you from listing this equation again, but we did it in every single lecture, right? Worst case compute time plus number of requests multiplied by your worst case delay, and this is repeated for every single resource, right? So you might have a summation over all resources here. So this is our frame of reference, right? This is what we call additive field. This is scheduling problem. This is I take interconnect, analyze it, put a term. Take caches, analyze it, requests might be hits and misses, and then basically put the total delay. Take the DRAM, I have some row hits, some row conflicts, some reorderings, and then I basically, there is a round robin, and then I put it, right? And then I sum everything up, right? This is maybe more or less a typical problem that combines all the three topics together, right? And we're going to solve a problem like this in next lecture. So this is your frame of reference that promises, and there are some proofs for this, that you'll be able to drive an upper bound on the total worst case action time if you analyze every resource separately and then you add them up. Good. Are we good? Okay, so I think by this we are done. We already discussed open versus close. And then this is the analysis thing, but I'm not going to walk you through that analysis. How much time do we have? Yeah. Yeah, this is more or less, in fact, this is a paper that we got a best paper award on, and I think 8 years ago. It was the first paper that enabled taking a very high performance memory controller and DRAM and drive a reasonable bound without modifying the architecture at all, right? So we took a best paper award in the most top conference in the field because, again, it's quite a complex math, but at the end of the day, the main point about it, it opened a new branch of why I need to redesign memory controller, because companies, ARM and Synopsys and Cadence, they don't want to redesign their hardware, right? They want to keep the same hardware, but they need to sell it for automotive market. We enable them to do this if you were able to run this engine in the background. Good. But that's the analysis part. You don't need to know anything about this here. If you're interested, I can give you the clue. Yeah. Can you guys stay quiet for a minute? Yeah. Sorry, can you raise your? Oh yeah, about lecture 7. So lecture 7, there aren't much of numerical questions that I can ask in the midterm without bringing in interconnect and cache and DRAM. Because again, the most interesting part about lecture 7 is this equation.
The second part
is this equation, right? So if I was to ask something in lecture 7, it's more going to be a theoretical question in question 1, right? For example, what are the two methods we do for analyzing stuff? Static analysis versus measurement based, for example, right? But there isn't a lot of numerical stuff. Most likely it's going to be in the final. Okay. Any other question or concern? Yeah, thank you. And again, we have the midterm on Wednesday until otherwise thing.